Picture an aircraft engine, 9 cylinders arranged in a circle, a crankshaft at the center. In every engine you have ever seen, the crankshaft spins, the cylinders stay still. The propeller bolts to the crankshaft. That is how engines work. Now forget all of that. The Gnome Omega ran the other way around. The crankshaft was bolted to the airframe and did not move. The cylinders, the pistons, the crankcase, all of it rotated around that fixed shaft. The propeller was bolted directly to the front of the spinning engine block. There was no intermediate shaft. The engine was the propeller, 9 cylinders, churning through the air at 1,200 revolutions per minute. And inside each of those spinning pistons, cut into the crown of the piston itself, was a valve. Not in the cylinder head, not operated by a camshaft or a pushrod. In the piston, a small spring-loaded disc of metal sitting in the face of the moving part, opening and closing thousands of times per minute, while the entire assembly spun at speeds that should have torn it apart. There is a question that follows immediately from this, and the answer is one of the strangest pieces of engineering in the history of powered flight. If the whole engine is spinning, how does the fuel get in? The answer is not what you would expect, and it took a pair of French brothers whose grandfather had built the country's first railway to figure it out. Louis and Laurent Sagan were not the kind of engineers who adapted other people's
long
ideas.
stroke and a compression ratio of 5 to 1, it initially produced this engine has a valve in the piston, which was automatic and operated without any type of command, mixed with the cylinders. At that time, not much was known about propellers, but it was known that placed by fixed radial ones. Since with the increased power in the years to come, not consuming oil, better understanding of air cooling and greater durability ended up
the company's entire focus toward a problem every aviation pioneer in Europe was trying to solve. Aircraft engines in 1908 were adapted automobile engines. They were heavy, unreliable, and they ran too slowly to produce useful power without becoming massive. The Wright brothers' engine produced 36 horsepower from 180 pounds. That weight-to-power ratio, 5 pounds for every horsepower, was the ceiling of what aviation could carry. Every aircraft designer in Europe was constrained by it. The engine was the airframe's enemy. The reason conventional engines of that era ran so slowly was cooling. Run an air-cooled engine too fast and the cylinders overheat. Add a water-cooled jacket and you add weight, which defeats the purpose. The engineering community was caught in the same loop. More power required more cooling required more weight required more power. Laurent Sagan's solution was to spin the cylinders through the air. If the cylinders themselves moved at speed, they would be continuously bathed in fresh air, regardless of how fast or slow the aircraft was traveling. The engine would cool itself at full power, at idle, and even while sitting stationary on the ground with the engine running, a condition that killed conventional air-cooled engines. The rotating mass also eliminated the need for a separate flywheel to smooth power delivery. The engine was its own flywheel. The cylinder walls on the first production Gnome Omega were 1.5 millimeters thick, machined from nickel steel, the strongest alloy available at the time, using the best American and German machine tools Laurent could source. The connecting rods were milled with deep central channels to eliminate material that added weight without adding strength. The finished engine, 7 cylinders, 50 horsepower, 75 kilograms. The contemporary alternative, a 50 horsepower Antoinette V8, weighed 145 kilograms, same power, half the weight. But the spinning architecture created a problem that no conventional engine had ever needed to solve. Fuel had to reach the combustion chambers. In a stationary engine, intake manifold pipes handle this without difficulty. In an engine rotating at 1200 RPM, intake manifold pipes would have twisted and failed within minutes. Some other pathway was needed. Laurent Sagan's answer was the hollow crankshaft. The one part of the engine that did not spin was the crankshaft itself, fixed to the airframe. Seguin machined it hollow. Fuel entered through the center of the stationary shaft, mixed with castor oil in the rotating crankcase below the cylinders, and was drawn upward into the combustion chambers, through the connecting rods and into the piston itself. At the crown of each piston, the inlet valve sat waiting. When the piston descended on the induction stroke, the partial vacuum it created was sufficient to pull the valve open against its spring. Fuel-air mixture entered, the piston reversed, the valve closed under its spring load. No camshaft, no pushrod, no rocker arm. The valve operated on nothing but the physics of pressure differential. If this is your kind of story, subscribe. We do this every day. The castor oil in that mixture was not incidental. Castor oil was used because it does not dissolve into petrol. Petroleum-based lubricating oils would mix with the fuel charge and burn through the engine in minutes. Castor oil maintained its lubricating properties even when soaked with raw petrol, even under the centrifugal force of a spinning crankcase. And even at the combustion temperatures, the cylinders reached at full power. The lubrication system was total loss. The oil went through the engine once and exited with the exhaust. Over 2 gallons of castor oil was sprayed into the air during each hour of operation. The cowling around the engine had the bottom quarter deliberately removed to direct that spray downward and away from the cockpit. It did not always work. Flying clothing worn by rotary engine pilots was routinely saturated with oil, and because castor oil taken internally is a powerful laxative, the pilots who flew these machines for any extended period suffered persistent gastrointestinal consequences that the medical reports of the Royal Flying Corps described with unusual clinical precision. The engine also had no conventional throttle. The Gnome ran at essentially one speed. To reduce power for landing, pilots used a blip switch, a button that temporarily interrupted the ignition. Cut the spark, cut the power. Release, power returns. The pilot's hand worked the blip switch continuously through the landing approach, cycling the engine on and off like a telegraph key. Misusing it at high power settings could shear the key that indexed the crankshaft to its mounting plate, destroying the engine and its mount simultaneously. These were the conditions under which the Gnome Omega entered the world's first international aviation meeting at Reims, in the Champagne region of France, on August 27, 1909. Henri Farman had been flying with an Antoinette engine producing 50 horsepower from 145 kilograms. Someone offered him the use of a Gnome Omega. Same 50 horsepower, 75 kilograms. Farman bolted it to his Farman Thrower biplane. On that single afternoon, he flew 180 kilometers in 3 hours and 5 minutes, winning the Grand Prix for the greatest non-stop distance in the history of aviation to that point. Louis Blériot watched from the crowd. His assessment of what the engine meant for the industry was direct. It enabled aviation to advance by leaps and bounds. By 1911, the French Air Force had formally adopted Gnome engines. By 1912, manufacturing licenses were being sold across Europe, to Britain, Sweden, Russia, the United States, and to a German firm called Motorenfabrik Oberursel, which would shortly be acquired by Anthony Fokker. By 1914, the Société des Moteurs Gnome held a third of the global aircraft engine market. The Omega design alone powered 60% of French aircraft. A single engine cost 13,000 francs, equivalent to more than 40,000 euros today. More than 20,000 Gnomes of all variants were built by the end of the war. 100,000 rotary engines in total were produced across all manufacturers and licensees. By some estimates, rotary engines powered 80% of all aircraft in the first half of the First World War. Half of the top 10 Allied aces flew rotary-powered aircraft. The Sopwith Camel, powered by rotary engines, including Gnome descendants, was credited with destroying 1,294 enemy aircraft, more aerial victories than any other Allied fighter of the entire conflict. But the Camel statistics carry a footnote that the victory claims do not. 413 Sopwith Camel pilots were killed in combat. 385 were killed in non-combat accidents. The Smithsonian Institution's summary of the aircraft is precise. Almost as many pilots were killed in accidents as died in combat. The rotating engine that had solved cooling, weight, and vibration had created a new problem in the air above the Western Front. The rotating mass of the engine was, by definition, a gyroscope. At 1,200 revolutions per minute, 9 cylinders of nickel steel generated angular momentum in one direction, with the force of several hundred kilograms of spinning iron. On straight and level flight, this was manageable. In a turn, it became a force that redirected itself relative to the pilot's input in ways that had no precedent in any ground vehicle or ship. Turning right, with the direction of engine rotation, was almost instantaneous. The nose dropped. The aircraft wanted to turn right. Right turns happened faster than the pilot intended them to. Turning left, against the engine's rotation, required effort and happened slowly, with the nose rising as the turn progressed. To fly in a straight line, a Camel pilot applied constant left rudder. To make a 90-degree left turn under combat conditions, many pilots found it faster to turn 270 degrees to the right instead. Experienced pilots described the Camel as having a tiger by the tail. Novice pilots, arriving at the front after training on docile aircraft, frequently found the gyroscopic response overwhelming. At low airspeed with full power applied, the top of a loop, a climbing turn at low altitude after takeoff, the engine could flip the aircraft into a spin before the pilot had time to respond. The Royal Flying Corps described the situation in a phrase that became part of the war's vocabulary. The Camel would give its pilot one of 3 crosses: a wooden cross, the Red Cross, or the Victoria Cross. None of this was the Seguin brothers' intention, and the engine itself was, by the standards of its era, remarkably reliable. Maintenance records from the Royal Flying Corps showed that a Gnome engine in a Newport 28 required 4 hours to overhaul. The Hispano-Suiza engine in a Spad 30 required 4 days. The Rotary was not fragile. It was dangerous in the air not because it failed, but because it succeeded. generating so much rotating mass that the aircraft around it became a different kind of machine from everything that flew alongside it. And then there was the German problem. Motorenfabrik Oberursel had licensed the Gnome design before the war. Fokker acquired Oberursel. The 80-horsepower Gnome Lambda, standard equipment in early French and British aircraft in 1915, was meeting its own licensed copy, designated the Oberursel UO, in the Fokker Eindecker, on the other side of the Western Front. The French Gnome in a Bristol Scout biplane and the German Gnome copy in a Fokker EI were the same engine. Same cylinders, same bore and stroke, same rotating mass, same castor oil smell in the cockpit. Two aircraft built on opposite sides of a war, powered by a design that neither side had fully invented, and both sides had built on a license granted before the shooting started. By 1916, the question was not which side the Gnome was fighting for. The question was how much longer it could fight for anyone. The Hispano-Suiza 8B produced 220 horsepower from 520 pounds. The Gnome Monosupape 9N, the most advanced production rotary in Allied service, produced 160 horsepower from 330 pounds. The rotary's weight advantage was real and it persisted, but the power gap had become decisive. A fighter powered by a Hispano-Suiza could climb faster, fly faster, and carry heavier armament than anything the rotary could push through the air. The Seguins and their competitors attempted larger engines, a 14-cylinder double-row rotary, an 18-cylinder version. The problems multiplied. The outer cylinders cooled adequately. The inner cylinders, buried in the assembly, separated from the airflow by an outer ring of spinning metal, overheated. No solution was found. The inner cylinders ran hotter, lost power, and failed faster than the outer ring. Multi-row rotaries were abandoned operationally before the war ended. The deeper failure was thermodynamic. In a conventional engine, the intake charge fills the cylinder efficiently through short direct passages. In a rotary, the fuel-air mixture traveled through the hollow crankshaft, through the crankcase, through the connecting rod passages, and finally through the piston valve, a long and tortuous path that prevented complete cylinder filling at higher speeds and higher power demands. Brake mean effective pressure, the measure of how completely an engine uses its displacement, was consistently lower in rotaries than in comparable inline engines. The rotary could not be made to breathe deeply enough. It ran out of physics before it ran out of ambition. By 1917, the Gnome was a trainer's engine. By 1919, rotary development had essentially ceased across every manufacturer in Europe. By 1920, the Gnome Omega company, as the merged entity had become, had no competitive new designs of its own and took out a license for the Bristol Jupiter to survive. The engine concept that had launched France as the global aviation power in 1909 was obsolete in 11 years. The Gnome Omega No. 1, the very first production rotary engine ever built, the engine that Henri Farman bolted to his biplane at Reims, is in the collection of the Smithsonian's National Air and Space Museum in Washington. It was given to the museum by Amédée Séguin, son of Louis Séguin, who co-invented it. A 1912 Blackburn monoplane, powered by an original Gnome Omega engine, is maintained in operational condition by the Shuttleworth Collection in Bedfordshire. It is the oldest known airworthy British-designed aircraft anywhere in the world. When it flies at air shows, it carries an engine that was revolutionary in 1909, that powered the first seaplane ever to fly, that gave French aviation its first world records, that went to war on both sides of the Western Front, and that killed a significant fraction of the pilots it was supposed to keep in the air. In 1932, 14 years after the war that had made it famous and then made it obsolete, two Soviet engineers built a helicopter and powered it with copies of the Gnome Monosupape. On August 14th of that year, the aircraft climbed to 605 meters, an unofficial altitude record for a helicopter at the time. The engine was already an antique. It did the job anyway. Laurent Séguin solved the cooling problem, the weight problem, the vibration problem, and the intake problem by inventing a new kind of engine. He could not solve the gyroscope problem or the beam-yep ceiling because those were not engineering failures. They were consequences of the same physical arrangement that had made the engine work in the first place. The spinning mass that cooled the cylinders also destabilized the aircraft. The intake path that bypassed the need for manifold pipes also restricted airflow at high power. The rotary's advantages and the rotary's limits came from the same source. It is not often that an engine's genius and its ceiling are the same thing. If you have heard an original Gnome Omega running in person, at Shuttleworth, at a museum, at an air show, tell us in the comments. There is nothing else that sounds quite like it.